General relativity, step by step. Got this nice formula here for the cosmic redshift term Z. Sometimes you'll see it written in terms of the wavelengths rather than the frequencies, and the wavelength being proportional to 1 over the frequency means that the formula turns upside down like that. That's just a different way of operationally defining Z. I'm going to go back, I'm going to pinch in a little bit here. I'm going to go back to my squared element, squared distance element, minus dt squared plus a of t squared dr squared plus angular stuff, which I'm going to ignore for the moment. I'm just going to consider radial motion. And last time I made the observation that if we were considering a photon, then ds squared equals 0 for a photon. So that tells me that dt squared equals a of t squared dr squared, which means that dt equals plus or minus for ingoing or outgoing a of t dr, which basically means that my slopes plus or minus a of t, my slopes of photon world lines. I've got this rather, well, it's not complicated, it is what it is, and I think I drew a picture. I've got a picture back here we go, and you can see I've tried to draw the slopes getting steeper as time goes by because of this relationship here. Well, that makes our life quite difficult, so what I want to do is to define a new variable t bar. That equals a new variable called conformal time. Conformal time, that's what that's called, and it's defined so that dt bar by dr equals plus or minus 1. So that means that light world lines are at 45 degrees, and that will make our life a lot easier. Okay, so how do we do that? Well, we basically need to say that dt equals a of t dt bar, and then if we go back to our rule here, then that's quite nice. Our squared interval basically says, our metric says that ds squared equals minus, no, I'll factor it this way, a of t squared times minus dt bar squared plus dr squared. This is for radial motion. And of course, that equals 0 for a photon. And I guess we could invert that to say that t equals the integral of a of t bar dt bar. A lot of people get confused by that bar over there. All I'm doing is expressing the scale factor of the universe a as a function of conformal time instead of as a function of regular time, and that's okay, I can do that if I want, but it doesn't really matter what this is. All I'm doing there is showing you that there exists an unambiguous relationship between these two coordinates, and again what I'm doing is exploiting the freedom of the Einstein field equations to use whatever coordinates make sense for me, and that's exactly what I'm going to do. Okay, so along a radial photon line, we've got that dt bar equals minus, let's say it's coming in, dr bar. And so that tells me that t bar, let's get this right, obs minus t bar emit equals minus r, oh no, not a bar there, obs minus r emit. And in the same way that I can exploit the freedom of the Einstein field equations by using a propitious coordinate system, I'm going to specify that that equals 0 because I'm going to choose the radius of the observation to be 0 because it's me that's observing it and I'm constructing my coordinate system about myself. It sounds like I'm picking out my location as special in the universe, and I kind of am. Well, I am, because I've chosen a coordinate system in which I am the centre of the universe, but anyone can do that. My friend on another galaxy, half the universe away, he can do that as well. So I am not violating the principle of homogeneity by this process. So I guess I can rephrase this as T bar emit equals T bar observed minus the radius of the place where the photon was emitted. You see, what I'm trying to do is, what I will eventually try and do is to link my observations just to my local coordinate system. That's what I'm trying to do in the long run. Now I'm going to go back to my equation for z, and I've got z equals a of t obs over a of t emit, but minus 1. I'll write that a bit more neatly. That's t obs over t emit. And I'm going to put a bar over it. Again, that is just a formal change. There's no content in that. I'm just thinking about what happens to the scale factor of the universe when I express it as a function of conformal time instead of regular cosmological time. I can do that. I can do anything. I can use whatever coordinates I like, and I'm just, for my own purposes, I'm going to choose these barred coordinates here. Equals. Minus 1, it's easy to forget that minus 1, plus a of t obs bar over a of, I'm going to use this formula here, t bar obs minus r emit. That's nice. That's z. So I guess you could say 1 plus z equals a of t obs over a, that's a bar obs minus r emit times a of t obs what am I trying to say here? Sorry, that should be a dot, where a dot is differentiation with respect to conformal time. I know I'm labouring this point, but it's important to do it right, because it's very, very confusing. 1 over 1 minus r emit times a dot of t bar obs over a of t bar obs. And we know that a dot over a equals the Hubble constant. Well, we're going to define it to be the Hubble constant, which I've mentioned a couple of times before. A dot over a equals the Hubble constant, and so what that tells us is that 1 plus z equals 1 over 1 minus r emit times the Hubble constant evaluated at the time of observation. H for Hubble constant is approximately equal to 1 plus r emit times the Hubble constant, t obs, and therefore z is approximately equal to the distance from which the galaxy emitted its photon multiplied by the Hubble constant evaluated at the current time. Part of the reason I'm being so careful about this is that you've got to be clear that the conformal time is a different beast from the universal time. But nevertheless, we've got this beautiful expression here for the cosmic redshift in terms of the Hubble expansion. Now, if I just go back to my definition that I had originally, or operational definition for Z, that equals lambda observed over lambda emitted, which equals approximately 1 plus v, where v is the velocity of recession, velocity of the receding of the galaxy, This formula here is just the Doppler shift. There we go. So what that tells me is that Z is approximately equal to V. Well, that's great. It's easy to get confused and to think, what? I'll just write it. I'll write out something that's wrong. In fact, I'll change to red. This is wrong. Z equals v. That's wrong. Because what I've done here is I've worked only to first order and I've neglected higher order terms. This is incorrect, and you can tell it's wrong because if we search for observed values of z, we get some very, very large values of z indeed. I think I've got a copy of Chrome open here. Just a minute. Yes, here's Google. Just a minute. Let me put my Google page there. Doesn't seem to want to move. Oh, here we go. And if I search for largest Z redshift ever observed, it'll probably point me to a Wikipedia page. Oh, here we go. Furthest galaxy yet smashes the cosmic distance. The redshift Z is 8.68. 8.68. Well above 1. And of course, if z equals 1, that corresponds to the speed of light. These are normalized coordinates. Just a minute, how do I... Oh, here we go. So, just a minute, I'll have to wake him up again. There we go. So, and this is, of course, I guess you could say that z is approximately equal to v over c if I wanted to put the speed of light back in. But somehow, we've got a z of 8.6, which is not equal to a speed of 8.6 times the speed of light. There's no equality here because this is only an approximate relationship, as you saw, because I used Taylor expansions and I used a whole bunch of linearized approximations to derive this result here. So the redshift is not equal to its recession speed. If we want to calculate the exact speed, then we need to go back to our original expression, which was that z equals lambda obs over lambda emitted plus 1 plus there, yes, and that's exact. So if we want to work out the actual speed of the galaxy as emitted, we need to use this exact equation here, and we need to specify that that's equal to a of t obs over a of t emit minus 1. But of course, to do that, we're going to need to know about the history of the expansion of the universe, because we need to figure out what this thing is and what this thing is here, and it was emitted maybe millions or even billions of years in the past. So we need to know about the long-term evolution of the universe, which I'll cover in the next screencasts. Stop there. Stop.